Hello again. Tonight we're going to talk about LOFAR and Starlink, and I'll get into what both of those things are. So you may have heard of SpaceX's Starlink constellation of several thousand low Earth orbiting data communication satellites. It's to provide high-speed wireless internet access. It doesn't provide directly Wi-Fi or 4 or 5G, but it provides internet access to rural areas or to underdeveloped regions on the planet. And they also have a more expensive service that provides it for RVers and for military operations, because if you really want to think about it, they orbit on multiple planes crossing over each other. So it really does cover the planet. The only two places they don't have continuous coverage on are the North and South Pole. But it's my understanding they purposefully put a couple that go circumpolar, a couple of satellites that go circumpolar to give periodic coverage to the South Pole. So they don't have continuous, but they have less than their previous sporadic coverage to the South Pole now. So that's good. But I also found out that in right here in Fort Lauderdale, which Starlink won't provide me internet access at my house, but they do provide internet access to an industrial park 10 minutes away from my house, where there's some data centers. Because Starlink is low latency, they can provide higher speed internet access than backhauling across the internet. If you are a Starlink customer, you can, as the saying goes, you can go from your house up to the bird, across to another bird, and then down to the station here in Fort Lauderdale. So that data center can literally knock the better part of 100 milliseconds out of each transmission. And if you're doing financial stuff or rapid deployment stuff, that's money in the bank, as the saying goes. So,
can I say something here?
Yeah.
In Mahwah, we've got a huge facility, which is Dow Jones,
Yes.
Wall Street
Yep.
industrial facility. It looks like Fort Knox when you drive up to it.
Oh,
It's
yeah.
completely concealed. And the same thing as on the Environmental Commission, we're always reviewing these towers being put up, and they're all about transmitting, as you said, the
Yep.
microwave data from point to point to point
Yep.
and saving milliseconds. And apparently milliseconds make a big difference.
Well, think about it this way. If you've got an automated solution for stock market transactions or for commodity market transactions, and you can get your buy or sell order in a fraction of a second sooner than your competition,
Exactly.
you can catch the high as it's high before it starts going low.
No,
So
exactly.
you can buy lower and sell higher than your competition if you have a few milliseconds off your transactions. So
Yep.
millions of dollars. So in order to have Starlink service, you have to have one of their ground terminals, which is a box, a long cable, and a little flat panel dish, and the dish automatically points itself as the satellites go overhead. So you got to have one of them things. And the box is a LAN router, so a wired cable networking provider. And it also gives you Wi-Fi, so you can get good speed access. It's not gigabit, so it's not as good as fiber from an access point perspective, but it is end-to-end faster by probably 30 milliseconds. So if you want less latency in your internet access, going gigabit gets you a faster connection, but you still have to go through all the backhaul routes to get there. And I know that Google and Microsoft and Oracle all have Starlink ground stations outside their data centers to trim off that internet backhaul latency. And you have to have an unobstructed view of the sky. So unlike where my house is, I've got lots of trees around it. The antenna has a shorter window of opportunity. So if it points over this way and goes, I can't get the satellite, I can't get the satellite, I can't get the satellite, I can get the satellite, good, 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 good. I can't get the satellite. So it's a narrower window. So I'm not going to spend $120 a month for something that is that fleeting, unless the world goes to hell in a handbasket and I need it as a catastrophic backup service. So LOFAR, or the station in the Netherlands is called, one of them is called Super Terp. Now, if you look at this, this is a giant ring of land surrounded by a moat. I don't know if the moat has anything to do with it, but it's surrounded by a moat. I think that's just to drain all the swampiness from the land because it's the Netherlands, but it's the low frequency array, or LOFAR. And you see all these different size squares, and they're all phased array radio receiving antennas for radio astronomy. And there are big ones that are really close to each other, and then there are smaller ones that are just kind of like shotgun blasts scattered around, but they're all in these patterns. The idea is to be able to receive from 10 megahertz all the way up to 240 megahertz as the Earth turns, because there's no moving parts here. As the Earth rotates, they can receive directly overhead, and because they have enough of these flat panels, they can do a synthetic aperture phased array. So they can tune the array to maybe, I don't know, 45 degrees one way or the other.
How do they compensate for Doppler?
Because each antenna can have a software backend that can put in an interjected delay.
Okay.
And I mean, we're talking nanoseconds here. I remember back working on computer designs, and yeah, when a signal had to propagate across a board, maybe 10, 12 inches from one side of the board to the other, the circuit that was nearby had to have a synthetically applied delay line, 4, 6, 8, or 10 nanoseconds, so that the two signals were in sync. But this is the same kind of thing. If you spot the little, looks like little obelisk buildings, little black buildings with a gray roof that are spread around, those are the actual receiving centers. So they're not too far from the receiving antennas, but the actual data center is nowhere near here. It's in a nice office business park. They actually have these sorts of collections of phased array receiving antennas in the Netherlands, in Germany, and in Ireland. So they can actually go from a small synthetic aperture to a synthetic aperture that is the size of several countries. So this is some pretty serious European money that they've invested in these arrays, in these radio astronomy facilities. That's LOFAR. Now
Go
there's
back.
go back. Okay. Yeah.
Because
Go back.
I'm looking at this picture,
Yeah.
and you're telling me that the center that monitors isn't located on there. So I'm thinking this is low maintenance. There's no people there except maybe the people that mow the grass.
Yep.
They're not having to maintain these things very much. Are they?
They go out to those little shacks that you see, the little black obelisk gray roof buildings.
Right.
To there periodically to adjust calibration on equipment. But yeah, it's this part of the observatory is fairly unmanned, and the data center that actually all the data routes back over fiber optic links, that's very well staffed. They might have 30 to 50 people there.
But not here on this property, right?
No,
There's not people there. And what are the little, the big squares are the low frequency, but what are the scattered little ones?
Oh, the high frequency and the low frequency use different size antennas. So you see the big tiles, the big black tiles, that's the one frequency range, and all the scattered brown ones, that's for a different frequency range.
Okay. Thank you very much. Now I understand that picture. Thank you.
Well, those are the kind of questions I really enjoy answering, because when I first look at it, I go, why do they need so many of them? And why are they different sizes? And why are they different colors? And yeah, I have the same questions myself. So when I get the answers, I'm very happy to share those answers so people don't have to go digging down the same rabbit holes that I do.
And I look at it and I think, how did they do the phasing correctly? But
fine tuning and calibrating. They have to have certain places in space that are known radio emitters in order to pick them out. So
I'm just saying, between antennas, how do you do the phasing? I mean, when we do ham antennas, we do a quarter loop phase,
now these are phased arrays.
way beyond like what people.
Yeah, these are electronically phased arrays. So I'm guessing that the black ones are very low frequency, And so you just put them close together because you're not going to be able to get much electronic swing out of them. The higher frequencies, the ones that are closer to 240 megahertz, those you have two goals. You have sensitivity and selectivity. If you want to focus the array sharply on something, then you use that sort of closer together bunch of little brown squares towards the center of one of the cells. And then when you want to get a big aperture to get a more detailed view of a large nebular gas cloud or something, you'll spread out the array to get larger and larger. And the fact that they have them in Netherlands, Germany, and Ireland, if you were to look at those on Google Earth, it makes an even bigger array.
No, it's cool. Let's move on. I understand the gain. I'm just the phasing is like what I'm questioning. But that's
there's a rabbit hole.
Let's not bore everyone with that.
There's a rabbit hole called synthetic aperture or synthesis aperture. It's literally about receiving all the data and then adjusting the phase of the received signals as the Earth is turning and as the speed of light is propagating the radio signal.
Got that. All right. That makes sense.
Okay, so there's another thing called the square kilometer array. And some of this is theoretical. They don't have it all deployed yet, but they've got a couple of like starter antennas and they want to build many, many more of them. They're right now like, we need more money. We need it to be more places. And we'd rather not have this recently discovered radio interference. So the square kilometer array, as the name says, it's a square kilometer of radio antennas, and their spacing varies based upon the particular radio frequency, but these are another synthetic aperture array. The Meerkat array has 64 antennas. The Mildura array, which is in Australia, has 64 antennas. And then the Murchison array in Australia actually has 22 groupings or tiles of each 16 antennas. And they want to like just blanket with 50 to 300 megahertz is one array. They have another array this is really broadband here, is 350 hertz up to 14 gigahertz. And they have another one that's a little less ambitious, which is 350 megahertz to 4 gigahertz. And they're looking in different areas because if you can observe a wide enough area and you have a synthetic aperture, all bets are off. If you suddenly discover some new physics or molecular chemistry in space, you can just tune it up. You don't have to worry about, we were only thinking around hydrogen, and that's a different frequency. So they're really going as broad a band with as many antennas and as many arrays as they can as a what if, because if they suddenly find something in molecular chemistry out in deep space, they might want to track excited oxygen instead of hydrogen. So they need the frequency agility and the large amplitude of large arrays in order to suddenly discover something and then tune into it. So that's why it's kind of a shot in the dark, so to speak. But they can use these in the daytime because they're radio antennas.
Wouldn't number two after hydrogen be helium as the byproduct of stars? Or
yes, but both hydrogen and helium, when they're excited, produce emissions at different wavelengths. So when you think about excited hydrogen, the one we always go for is the like 1.2 gigahertz or whatever it is.
Right.
But there are other emissions of hydrogen. The optical astronomers, they shoot in hydrogen alpha, which is closer to infrared. It's a really dark red. But the other wavelength that radio guys shoot at, you can't see because it's gigahertz. So, the same hydrogen atom being excited to different energy levels will produce different wavelengths out. And some of it is close to red, close to visible, and some of it is way up there, like, above ultraviolet.
Every radio frequency has harmonics too. So
yes. And some of them, they like the James Webb Space Telescope has a very narrow infrared band. So some of the things they observe on their spectrometers are not primary frequencies, they're actually harmonics of the chemicals that are being excited. It's what
I have
you
a question. Question?
Go for
I have
it.
Okay. It says on your second sentence says multiple different size and design of ground-based synthetic
Mhm.
aperture. Now, my question is why do they have? I mean, is there anything that is not synthetic aperture out there? I mean,
Yes.
aren't they all?
For example, the Deep Space Network, the NASA Deep Space Network, where they communicate with space probes out in space, they don't use those for synthetic aperture all that often, because what they want is a very high quality, high amplitude signal of something that is reasonably high energy when you compare it to cosmic phenomenon. So they'll use one antenna to point at James Webb Space Telescope.
Okay, you're going over my head here.
Yeah,
Over my head.
whereas if you're observing something in nature, the amplitude of the signal is going to be down to billionths of a watt.
Okay, so it would be based on it's saying synthetic versus nature, right? But do they have
No.
Or-
It's in synthetic versus direct. If I'm receiving my signal only on one antenna, that's direct receiving. If I glue the signals together over several antennas, that's synthetic aperture. If I have different regions on planet Earth that have arrays of antennas and I glue all of those together, that's called very long baseline interferometry. The mathematical process of synthetic aperture is called interferometry.
So there is nothing natural, nothing out there that does this naturally.
No, they're referring to it as synthetic because it's a signal that did not exist in nature. They didn't have one receiving antenna that was 4,000 miles across. They had maybe 24 antennas that were spread around the planet with 1,000 plus miles between them.
So they're putting, so these gaps that come in between them are filled in the sense?
Yes, that's the part about synthetic. They're creating mathematically, synthetically, an antenna that is that big.
I was thinking they were comparing it to something in nature. I'm going, there's nothing out there in nature that does. Okay. All right. So this is good to know. Okay.
Yeah.
Thank you.
I like the questions because when I edit this for public consumption, there are people out there that go, what's astronomy? Or, you know, they're not as versed as someone like myself, and they have questions. And if they have questions, it's probably something I've already investigated and have, pull the flap up and it's off the top of my head.
And I just make up stuff just to mess you up. That's it. So.
Well, people have said sometimes I make some of this stuff up. That's why I put all the links at the back of the presentation.
All right. Good night, guys.
Okay. So you may have heard of Dark Skies or International Dark Sky Association, which, by the way, they recently changed their name to just Dark Sky because the International Dark Sky Association apparently was a mouthful. So they felt they could market themselves better just by calling themselves Dark Sky. Okay. But now that's against light pollution and astronomical imaging and maybe health effects associated with light pollution. So dark sky. Well, that's with lighting. There was a similar set of initiatives associated with radio frequency pollution, all the radio hash noise that we as an electronic society are producing. And that's referred to as quiet skies or radio frequency interference. And Dark Sky has a program called Dark and Quiet Skies. And the International Astronomical Union picked up on that buzzy phrase, dark and quiet skies. And even the International Electrical Engineers Organization, the IEEE, of which I'm a member, I'm a software engineer. They've picked up on dark and quiet skies. It's a thing. It does interfere with astronomical observing both in imaging and radio. So it's something to think about. And if it's a problem, find a way to mitigate it. So the first thing that people have to know is you need to stay within your allocated frequencies. The U.S. Federal Communications Commission does give you channels that you've requested, if they approve them, for your radio transmitters. So you don't just send up a satellite and you stomp on somebody else's frequency. You say, hey, I'm sending up a satellite, or 22 satellites in the case of a Starlink launch. I've got 22 satellites I want to send up. I need some frequencies. FCC, please allocate. And they have to file a bunch of like paperwork. I've heard that it's about 70 pages of paperwork per satellite that they have to file whenever they launch satellites to explain where the satellite's going to be, what frequencies it's going to transmit on, how many watts over the curvature of the Earth. Do they know not to transmit over certain areas like radio astronomy observatories? And all that stuff gets factored in before they get their approval. So they don't just go rogue and transmit wherever they want. You might not be aware, but the FCC already has established power levels for Wi-Fi transmitters and Bluetooth transmitters and mobile phone services and cordless phones and the little radio frequency ID tags that are your SunPass transmitter and such. There are frequencies that are allocated for these things. They're approved. If you're a standards group, you have to ask for frequency use. You have to get it approved internationally. And so you don't just transmit on wherever you want with whatever power you want. You have to sort of stay within your lane. That's the official allocated frequencies. The FCC already works with device manufacturers to curtail spurious or unintended, not purposed or deliberate radio transmissions. And if you've ever seen a piece of electronics, it might have a plastic case on the outside, but on the inside, it's got these like aluminum or steel panels that cover over certain parts of the electronics because it's trying to stop the spurious or unintended radio transmissions coming off of certain parts of the electronics. And so in order for an electronic device to get its FCC registration tag, that little FCC logo they put on products or packages, they have to test their product, shield its innards from producing unwanted radio transmissions. So if you go buy yourself a router and you put it in your house and you want to go listen to AM radio, the router should not be transmitting on the same frequencies, even if unintended, as your AM radio. But they will occasionally do because not all this stuff is registered through the FCC and you're going and buying it from some other country. And so you have to worry about spurious transmissions. And the FCC actually produces a little text on how you deal with this. And the first thing you do is the device FCC registered? If so, you can file a complaint with the FCC. If the device is not FCC registered, how did you buy that from within the US? How did you get it imported? The FCC is an inquiring mind that wants to know. Whenever Starlink sends up some satellites, they have assigned channels for uplink and downlink frequencies. Whenever you have a Starlink terminal that you put out in the back of your house or on the roof of your house, you have known frequencies that you're transmitting up to the satellite and receiving down from the satellite. All this stuff gets registered and your test results gets logged with the FCC, so you're not producing unwarranted spurious transmissions. And if you ever looked at an FCC frequency allocation chart, you'll see that it goes from 0 hertz all the way up to about 3 gigahertz. Left to right, top to bottom, the frequency goes up, the wavelength gets shorter, and all those little colored boxes are reasons why a frequency range is allocated. And if you see on the left side of the chart, I'm not going to get into all of them, but all those little different colors represent different purposes for those frequencies. And if you look, the wide bars, those are the frequency ranges, and some of them have different color bars stacked vertically on top of one another. Those are shared frequencies. Whenever you have limited transmitters, you can allocate shared frequencies because they're not going to be stepping on each other because they're transmitting in different directions or at different power levels, and they don't interfere. So they share the ride. You'll also note that as you get from the low frequency to the high frequency, those little vertical columns get narrower and narrower and narrower, because if you want to transmit more and more information, you've got enough waves, because it's higher frequency, that you can put more data in it and you don't need as wide a channel. But why did they stop at 3 gigahertz? That's because at 3 gigahertz, you start getting into light. You start getting into the lower, longer wavelength, lower frequency, longer wavelengths of deep infrared light. And that gets in another turf. That gets into the Food and Drug Administration's turf, because the FCC does all the radio frequency stuff, but the Food and Drug Administration, they deal with lasers and X-ray and UV and gamma and microwave ovens. And oh, that's right, there's a notch around 2.45 gigahertz where the FCC governs microwave ovens. So the microwaves that could bother your cells get covered by the FDA, and the frequency that the microwave oven transmits its microwaves on is governed by the FCC. So on the back of your microwave oven, you'll see FDA registration and FCC registration. So I want to make sure none of that spurious stuff happens. So if you have somebody that's deliberately transmitting off their allocated transmission, or they're not appropriately shielding their product to not produce spurious stuff, you can complain to the FCC. They have a complaint site. They will send out a vehicle that has a bunch of antennas on it, and they will go roaming for the offending emissions producer. If they're stomping on somebody else's frequency, like some hacker is transmitting on an FM radio channel at some other station's frequency and stomping on them, the FCC will give them a kind knock on the door and say, cut it out or else. And the first level of or else is they confiscate your equipment. The second level of or else is fines. The third level of or else is you can be arrested and go to jail. Stay within your lane, otherwise the FCC come a knocking. But what about offending receivers? What if I'm wanting to receive something on a frequency allocated to something else? Like I want to receive weather satellite transmissions because I want to produce my own weather maps. You can do that. What if I want to receive, police calls on a scanner? You can do that. What if I want to receive satellite broadcasts from DirecTV? That's illegal, because they've got an arrangement that channel is for profit. And if you as a receiver find a way to receive their encrypted signal, even if it's not for profit, that's considered an offense. And I don't know how they're going to know you're receiving, but that's considered an offense. Now, if you happen to be in the U.S. state of Virginia, if you have a vehicle speed radar detector, they can confiscate it, no questions asked. They won't even fine you. They'll just go, I can see you have a vehicle radar detector mounted below your rear view mirror in your car. Give that to me. And in the state of Virginia, they can confiscate it. So let's say that you're into radio astronomy and you want to receive a frequency that just you chose that frequency. If you happen to choose a frequency that is a spurious transmission, and that transmission is within the FCC's transmission power limits, there's nothing for you to report, because its transmissions are within the defined limits for spurious transmissions. The fact that your radio astronomy receiver is amplifying it by 1 million times doesn't allow you to complain that they're transmitting too loud. The requirements to constrain this stuff is to make sure we don't step on other things. But if you have spurious emissions of a satellite that pass the ground-based limits, then they can put up something in space that their purposeful transmissions are on the channels they're supposed to be. Their unintended transmissions are well within the ground-based spurious limits, but once you put it up into space, if your radio astronomy observatory cranks up the amplification, that will be a much stronger signal, even though it's within legal limits, than your celestial deep sky object. And so that's what happened. LOFAR said, we don't like all these Starlink satellites. And why is that? It's not because the Starlink satellites are transmitting off their allocated and registered transmission channels. That's okay, because they're allocated those. It's that spurious transmission stuff that when the radio astronomy observatory amplifies the signal by 1,000,000 times, they can detect the Starlink satellites at a much stronger signal level because they're just in low Earth orbit than the deep sky stuff that might be, nanoamperes, 1,000,000 light years away. But they can't detect them continuously. So if you look at this particular spot diagram, you'll see that, oh, by the way, it's the degrees, you see they're going from 0 up to 1.5 and down to minus 1.5. Remember me talking about the phased array being able to electronically tilt the antenna? This is looking straight overhead as the Starlink satellites go by over a 50-minute period. That's why you see multiple green circles there, and why you see the one that's brightest, the darkest green one, is directly overhead. The satellite goes overhead. The particular frequency they're looking at is 150 to 153 megahertz, which is way lower than the actual gigahertz. It's probably around 8 gigahertz allocated transmit receive channels. So the spurious transmission of the Starlink satellite that is just fine when they tested it out on the ground, when it crosses overhead of this high power radio astronomy observatory, they can pick them up. And that's what they're complaining about, is your spurious transmissions are being received by our radio astronomy observatory. And if you think about it for a moment, when the Starlink satellite is going over a radio observatory, they turn off their primary transmitter because the radio observatory can receive in that range, and they don't want to blow out the receiver by putting a 20-watt signal through it that gets amplified by 1,000,000 times. So they know to turn off the intended transmission as they're going over radio astronomy observatories. But there's nothing they can do about the unintended spurious transmissions that are very low amplitude that get very high amplified by the observatory. So that's what their complaint is could you just somehow stop putting out any electronic noise whatsoever when you cross our observatory? And they're not violating any current rules. And aside from just turning the satellite completely off, how would they know how to turn it back on again? No way to get rid of spurious transmissions. So as I was saying, the amplitude of celestial transmissions like quasars and such, those are in the billionths of a watt range. When the satellite goes overhead and its intended transmissions are turned on, those could be 20 to 50 watts. But even when they turn those off, their shielded spurious transmissions might only be millionths of a watt. But when you've got, cryogenically cooled receivers at your radio astronomy observatory, and you amplify that millionths of a watt by billions of times, you might blow out your receiver. So what's weak on the ground, but when you put up in space and then you amplify it considerably, gets very loud. Think of it as a person being deafened by somebody whispering 5 miles away because you amplified the audio 1,000,000 times. Try calling law enforcement and complaining that someone's being too loud. I don't think that's a law enforcement issue. I think that's a regulatory issue. And that's what we're talking about here. Regulatory, not enforcement. So there's a saying, a lot of a little is a lot. So if you have a very small amount of spurious transmission from a few thousand Starlink satellites, that could be a problem, especially if there's a lot of them going overhead. The summation of all those spurious transmissions may cause your radio astronomy observatory a problem. How do you deal with this? And this is where the left hand and the right hand need to start talking to each other. So we've got this organization in the US called the FCC, the International Astronomical Union, also works with one called the ITU, the International Telecommunications Union, to do frequency allocations. So the FCC is going to allocate transmitter stuff. They're going to contain spurious stuff. Expecting the spurious stuff to be zero is that's just not going to happen. You cannot contain all the radio emissions because then your product becomes too heavy and there's too much shielding and such. A radio astronomy observatory is going to have a quiet zone around the observatory where they can actually police the actions by local Wi-Fi or Bluetooth or mobile phones or computers or microwave ovens. If you've ever looked at the Green Bank Observatory in West Virginia, they have policies on if you get within range of the antenna, you have to turn off your computer, put away within a radio protective bag your mobile phone, because even when your mobile phone's turned off, it's still transmitting emissions, spurious ones. Starlink's not a rogue operator. They're not a third hand. They do work with the FCC, and they're willing to listen to and investigate complaints and attempt to mitigate them. The FCC is coordinating with international organizations, but they also need to coordinate with astronomy observatories on spurious transmissions to maybe get those lower. But you're not going to get something into the billionths of a watt so that it doesn't compete with celestial things. And also, there are frequencies that are allocated for lawful transmission for other purposes than radio astronomy. And, a radio astronomy observatory can't develop these very broad receiving ranges and just pick what they want to receive on when something else has already been allocated to lawfully transmit on it. They can't just go, hey, we found something new and different in the realm of chemistry and physics, and we now want to receive on, 2.4 gigahertz. Well, Wi-Fi's been allocated that for a long time. You're not going to make all the Wi-Fi on the planet suddenly move somewhere else. The best solution for that is put your radio observatory in space above the Earth. So think about cooperative solutions. They can cooperate and say, we'd like to be able to do radio astronomy on certain frequencies. And then you can work with the FCC and with people that manufacture things and improve the protection against spurious emissions in those ranges. And you can make sure that the FCC doesn't allocate or maybe doesn't share in those certain ranges. And so you could now have equipment manufacturers that produce products that don't produce as high an amplitude of spurious transmission. But you got to stick to those frequencies, you radio astronomers. You can't come back later and say, hey, we found out something new, and now we want to listen in on a different frequency that's been allocated to something else or is within the constrained limits of spurious transmissions. So the communities do have to cooperate with one another, internationally even. But I've got to say that the most recent complaints by LOFAR and SKA, I did some scrutiny on those complaints, and it looks like they're only complaining about Starlink. And it's in Starlink's best business interest to pay attention to these things and not, have an irate radio astronomy community against you. But there's a whole bunch of constellation satellite programs that are out there that are transmitting on FCC allocated frequencies, but also have spurious transmissions. And they have much larger, more powerful electronics than does Starlink satellites. Starlink is in the mass manufacturing business. They don't want to make the electronics of the satellite any more powerful, any more capable than they actually need to do. That's why satellite to satellite, they move from radio frequency communication to laser communication. But you can see this laundry list here of other companies, direct competitors of SpaceX Starlink, that LOFAR and SKA aren't going after them because they want to establish the ground rules using Starlink, a willing contributor that's listening and willing to change. And once they get that stake in the ground, then they can go back to the FCC and the ITU and say, all these other guys have to follow the same rules. And that would work, except for the fact that the US doesn't have jurisdiction over non-US, and you have internationally non-US, non-agreeing companies. You have small islands out in the Pacific that are independent nations that don't belong to the ITU, and transmit on whatever frequency you want, because your intended frequency is just directly down to that particular small nation. They're providing, internet access to just Tonga or someplace. And then you have organizations that should know better, but don't, like international spy satellites, they're surveillance satellites. They get frequencies from the FCC, but they have huge amounts of electronics, and nobody's going to curtail their spurious transmissions. They're going to put some metal on the outside of their satellite. Good enough. You can't make it go to zero, no matter how much you try. Here's a different approach, and this one requires some investigation into the physics of it. So we know that we have filtering for optical astronomy. We can say, I put a red filter on it, so all I got was the wavelengths associated with a certain band of red, or green, or blue, or ultraviolet, or infrared. So that works in optical. Everybody knows that as the universe expands, things get red shifted. So if a radio signal were coming from a local source, like something low Earth orbiting, its signal would not be very much red shifted because it's so nearby. But a galactic radio source that's out in space, a million light years away, if you're receiving on the same frequency, that frequency is going to be red shifted. If radio astronomers would have a much tighter band and much finer tuner frequency, they could say, if I've got a satellite that is producing spurious emissions at 150 megahertz, and I want to receive at 150 megahertz, it wouldn't be precisely 150 megahertz. The low Earth orbiting stuff would be 150, because that's electronics that are driving that. But the celestial radio frequency coming down that you want on 150 megahertz from a chemistry perspective would be slightly red shifted because it's far away. So if they would dice up their band finer and make their receivers easier to tune on off frequencies, they might be able to avoid some of the emissions that they're now saying they cannot deal with. Look into a physics-based solution. If you don't think that works, when they first put up the GPS satellite constellation network, they were good within 125 feet, but then they considered Doppler shift as the GPS satellites were moving at 23,000 miles an hour plus as they go around the Earth, and they took into account the Doppler shift of the radio transmissions from the GPS satellites, and that's how they got it down to 75 feet. And then through multiple satellite triangulation over more than 3 satellites, and the timing of the signals down to a fraction of a second, that's how they got down to 25 feet. There are things you can do in the physics of your radio tuner when you digitally receive things that you can tune pretty precise signaling. And I think that radio astronomy needs to take a look at that, in my humble opinion, as the saying goes. So in conclusion, yes, I comprehend the issue for which radio astronomy community is raising the complaint of interference. When you're transmitting within the bands assigned to you, that's fine. If you're transmitting on a band not assigned to you, there's legal ramifications associated with that. A spurious transmission that is okay when they're examining it ground-based, but not okay when it's been amplified by millions to billions of times, that's some area that they need to take a look at it. And maybe they can make more shielded devices, but you have to wait until they put those things up in orbit, which could be a couple of years. The communities, both the regulatory and the astronomical, have to work together to figure out how we get a handle on spurious transmissions, and then maybe take a look at some temporal physics means of finer tuning the receiver to get locally transmitted stuff from Earth orbit filtered out from the stuff that's coming in from millions to billions of light years. And links. Comments? Questions? Too detailed? Hey, there was no math. Was that
Did you say that cell phones put out spurious signals even when they're off, powered off?
Yes, they do.
Ooh,
Yes.
that's creepy.
Think about it this way. It's been many a decade since the power on off button on your phone was mechanical. It's a capacitive touch button. How does a capacitive touch button work if there's no power?
Good point.
The electronics in your phone are actually powered on when they're powered off.
Thank you.
Wow, we're going to end early tonight. Any other comments or questions, or would you like me to turn off the recording so we can go off topic if you want to?
Sounds good.
Okay, I will stop recording.